All right, guys, so let's talk about sex-linked genes. Sex-linked genes are, by the way, also called X-linked genes. These terms are used interchangeably. So our case study for here is Alexis Romanov, who was the son of the last Tsar of Russia, Tsar Nicholas and his wife Alexandra. He was a hemophiliac. So hemophilia is when blood does not clot. It keeps bleeding, right? So it can keep bleeding externally, or it can happen more problematically internally. This is caused by a mutation in a gene for a clotting protein that helps your blood clot and stops bleeding in most of us. This is a recessive allele, and this is found on the bottom of the X chromosome. Remember, the X and Y chromosomes are going to be our sex chromosomes. And because the Y has no corresponding allele, the Y is just like a little nugget of a chromosome. This presence on the X chromosome means that if you are a biological male and you have the recessive allele on your X chromosome here, you don't have anything else on the Y to balance it out. There's no other options. This is all you get, and so you have to express it. If you don't have that allele, then you just have a normal allele and you have normal clotting factors. Males cannot be heterozygous for this because they only have one X. So this is why they're also called X-linked. So Alexis did not get his hemophilia from his father, Tsar Nicholas, because his father was not a hemophiliac, and because his father was also biologically male, he would have to express it if he had that allele. Okay, because biological females have two X's, they have two possibilities, which means that they could have both normal alleles, as shown here. They could have one of the recessive alleles and one normal allele, or they could have two recessives. For a biological female, you're going to need to have both of those recessive alleles to be a hemophiliac. You need to not have one good copy of that gene. So women or biological females can be either homozygous or heterozygous for hemophilia, but biological males they're only going to need to have one allele, and they're going to express whatever one they get. And they're going to get that X from the maternal line. So it is going to be always the maternal line is where the hemophilia is coming from. So Alexandra, she was in fact a carrier of hemophilia. And you can see that she had 4 daughters, Olga, Tatiana, Marie, and Anastasia. And we don't know if they were carriers or not, but we know that they were not hemophiliacs. And we know that Alexis was. So the deal here is that as the boy, male offspring, he suffered from this hemophilia. This led to a lot of problems in the Russian Empire, including allowed Rasputin to come in and make himself cozy with the family, because Rasputin was sort of a mystic, and he was supposed to be able to help out with Alexei's bouts of hemophilia. He was going to cure him. So his mother, Alexandra, who they called her Alex too, she let Rasputin hang around, which led to some problems. And of course, all of them were assassinated by the Bolsheviks, which was in 1918 or something like that. Okay, so problems. Genotypes. It's going to be a little bit different than what we were used to. This is the real reason you're watching this video. Instead of having our hemophilia allele just by itself, we're going to put everything on the X or Y. Okay? So the X carries that gene, which means we put our little tiny X, our little tiny H, our recessive hemophiliac allele. We're going to put that on the X there. A hemophiliac female is going to have a little H on each of those X's, and a female carrier is going to just have it on one and have a normal big H on the other. A male without hemophilia is going to have a big H. Nothing goes on the Y. We don't ever put anything on the Y. The Y is naked. Okay. And a homozygous, no hemophilia female, big H's all around. So if we cross the parents, the Tsar, he's got a big H and a Y. Tsarina, she's got, that's Alexandra, she's got a big H and a little h. And then there's all these possibilities. So they could have a daughter who had two big H's. They could have a daughter who is a carrier. She has one big H and one little h. They could have a son who is not a hemophiliac, or they could have a son who is a hemophiliac with that little h. So the only way that you're going to be able to get a female hemophiliac is if the mother is a carrier and the father is a hemophiliac. So you have to have a hemophiliac father. And this is pretty unusual before modern medicine because most males who had hemophilia did not live long enough to have offspring. They died young from complications from the hemophilia. All right, good news is that we now have a bunch of different ways to treat hemophilia. There was a lot of issues with hemophiliacs during the AIDS epidemic because what happened was during the 70s, they gave a lot of blood transfusions with blood that was HIV positive and infected a bunch of hemophiliacs. So that unfortunately cost a lot of lives before we knew what was going on there. And then we were able to come up with some various treatments for it, including now gene therapy, which is super effective at treating hemophilia. All right, other X-linked genes. So this one, don't say what it is. This one, you guessed it. Here's another one. Ooh. Other X-linked traits are color blindness. That is also on the X chromosome. We are going to see many more colorblind males than we see colorblind females because if you're going to be a colorblind female, that means you have to have two recessive alleles, which means that your paternal line, your biological father, would have had to have been colorblind in order for you to be colorblind. Again, biological females are going to be the carriers here for colorblindness, and if a male has the recessive trait, he's going to express being colorblind. So here's all your different genotypes here. Fruit flies are our favorite little thing to look at when it comes to these X-linked traits. Turns out that the eye color of fruit flies is caused by a mutation on the X chromosome. So these like little ghost-eyed, white-eyed fruit flies are the mutants here, and we set up their genotypes to look like this. You can see that our male with normal dominant allele here is going to have red eyes, and the small w is going to be a white-eyed male, and then we have a white-eyed female and heterozygous carrier female and a homozygous red-eyed female. So again, to be this white-eyed female, your biological father fly has to be white-eyed. So, and then there's sample problems. When you're crossing these, you just got to make sure that you're keeping track of what is on the X and you're not putting anything on the Y. Don't put things on the Y. That's one of the things that people do. Most common mistake is putting things on the Y. All right, you guys, that's it. That's everything you need to know about sex-linked problems, do those problems in your genetics handout and make it happen.